MOSFET IV model. And here we derive the two important equations for the triode region and the saturation region. So those are the current versus the gate voltage and drain voltage equations. And then we have two curves. One is ID versus the VDS. The other is ID versus VGS. So here we have those two equations and two curves. Further, we discuss the operation region depending on the voltage. So here you want to determine the transistor's operation region. First, look at the gate voltage compared to the threshold. And then above the threshold, further we need to compare the VGS minus VT, which we call it VOV, the gate overdrive. And then you need to compare this VOV with the VDS. So if VDS larger than the VOV, then it's in the saturation. And then we said that in the saturation, the transistor is more like a voltage-controlled current source. And then if the VDS is smaller, VDS is smaller than the VOV, then the transistor is in the triode. And then we said the transistor can be approximated as a resistor if the VDS is very small. And then the resistor's resistance is given by this formula. And then we talk about the parameters for the IV equation, and here we have some notations from that Cetera-Smith textbook. Like the Kn prime is defined as this mu n CoX, and then if you further include the W over L, which is the geometry parameters, then you get the Kn. So this will be a simple version of the saturation current. Drain current is half Kn, VGS minus VT squared. So this is also called the square law of the saturation current. And then we have this example, and I put down the solutions for the example here, and you can check after class. And then we briefly talk about the second order effect. This is channel length modulation, which explains that the drain current actually does not saturate even in the saturation region if you consider this channel length modulation effect. So basically it says that after the pinch-off point will move to the left if you further increase the VDS. So effectively the channel length L is reduced when you further increase the VDS. So that will translate to a larger current. So the current will further increase with VDS, and then we use a lambda as a coefficient to represent this relationship. So here, then you will see this kind of increase of current even in the saturation region. And if you trace back all those curves, this is with different gate voltage, but if you trace them back to the negative side, then you get this early voltage. And this early voltage with A is 1 over lambda. So as we said that in most cases in this class, we will not use this equation for calculating the currents for the digital circuits. But if you take any analog design classes, maybe later, then you will use this or not, because in the analog design we operate on the slope of this ID versus VDS curve. So I will not talk about too much details of the analog design. Yeah.
Then, so in band diagrams, the channel is determined by what? The PN thing? When we have a band diagram, in a band model, how do we determine the channel length?
So that's a very good question. So, so in the band model, we don't really define the channel length in the band model, right? So the channel length is given by the geometry of the transistor. Here, this channel length is the effective channel length. So it's effective channel length. And then we only consider this in this pinch-off model. We didn't have this kind of effective channel length in the band model. In the band model, we will describe this as the lowering of the barrier top towards the source side. So they are equivalent to describe the current further increases with further increase with the drain voltage, but from different physical pictures.
So you're describing the same thing in two different models.
Yes.
You're saying effectively the channel length will be imagined as lower. And
Yes.
second case is saying that actually the band is lower.
Yeah. All right. So then let's start today's discussion. So here we have one example to determine the DC bias current of this transistor. So here we have this circuit with 4 resistors and 1 transistor. And here the question is to ask to determine the voltage at all the loads and the current through the branch. So basically it asks what is the voltage of this node, and this node. Basically those 3 nodes are the VG, Vs, and Vd. And also we want to know what is the ID, the current flow from the transistor. So here the resistance are all given, and the transistor's threshold voltage 1 volt is given. And then this Kn parameter is also given. So here ignore the channel length modulation effect. How do we approach this question?
There will be no current in the gate terminal.
So yes, the gate is insulating, so there's no current flow into the transistor from the gate. Current only flow from the drain to the source.
So we know the VG.
So the
like
VG here is easy to be determined because this is a voltage divider through those transistor 10 mega ohm. So this is like voltage divider, and then the VG is easy to be determined. So here in this example, the VDD power supply is 10 volts. So VG will be half, 5 volts, because here are 10 and 10. So then VG is 5 volts. Okay. Then here the challenge is to determine the Vs and the Vd. So you don't know what is Vs, you don't know what is Vd. Actually, it's very hard to determine the transistor's operation regime because you need to know VGS to compare with VDS. Right. So here, since we don't know, we have to assume something, or let's say guess. So let's assume the transistor is in the saturation. So if the transistor is in the saturation, you know you can apply this saturation current. This VGS minus VT squared. You can apply this equation for the saturation current. Okay, so but here the challenge is that we don't know VGS. So we have to look at this circuit. So what is VGS? We need to know what is Vs here. So here you see this branch, we have ID. This current will flow through the 2 resistor, RD, RS, and this transistor. So they will be the same current, because current is continuous. So then the voltage drop across the RS will be this RS times ID. That is the Vs, right? So similarly for the Vd, this node, what is the Vd? So it will also have a voltage drop across the RD here. So that means here you will have VDD minus RD times ID. So here you start from VDD, and then you will have voltage drop across this transistor, this resistor. This resistor RD, ID will be the voltage of the resistor RD. So you have VD equals to this VDD minus RD, ID. So here you don't know what is ID, so you have to look back to this equation. You need to plug in the VGS in this equation. So you know VGS is VG minus Vs. VG minus Vs. So here we use VGS. So G first, S second. means we are going to use S as a reference. So it's Vg minus Vs. So what is Vg minus Vs? Vg minus Vs will be this 5 minus Vs. Vs is Rs ID. So let's plug in the numbers. So Rs here is 6 kilo ohms. Let's use 6 ID here. So here we are going to use the 6 kilo ohm for the Rs. And since we skip the kilo here in the notation here, so that means when we solve for the ID, it will have a unit of million. But the question is how many? So let's plug in this to this ID, this equation. So ID equals to this half Km prime W over L. So it will be half. And Km prime W over L is given is 1. And here the unit is milli, so let's skip that. So then later we will know that the current we solve will have the unit milli. So it's 1. And then times VGS minus VT. So what is VGS? VGS is the VG, which is 5 volts, minus S, which is this 6 ID, this low, 6 ID. So this is the Vs. And then minus Vt, the threshold is 1 volt here. It's 1 volt here. And then square. So you look at this equation. You only have unknown, that is ID. You can solve for ID. So let's move the terms out. You will get 18 ID square minus 25 ID plus 8 equals to 0. So if you rearrange the terms and then you make it as a standard second order equation, you have this first order and then second order term, first order term, and then the constant value. Then you can solve for this equation. I think this is like a middle school math. So let's do that. You have two solutions, right? This is the second order equation. So you have two solutions. So one is ID1 is 0.89 milliamp, and ID2 is 0.5 milliamp. So here is weird, right? You have two solutions, two currents. So how do we resolve this problem? Any idea?
Just complete Vs and Vd.
So you need to verify your assumption, right? So here you assume a saturation, but this is what you assume. You need to verify. So you need to plug in this ID back to the Vs node here. So because Vs here is Rs times ID, which is 6 kilo ohm times this ID. So if you plug in this back, you will get the first Vs. It's 5.34 volts. Then you find out this is invalid because gate voltage is 5 volts. If ID is this 0.89 milliamp, you get Vs 5.34 volts. So the VGS actually is negative. So this transistor is off. This is NMOS transistor. So this transistor is off. So this is invalid. So you should discard this solution. So the second one, if you plug in that, you will get Vs2, 3 volts. So here you will have 3 volts and 5 volts. You can verify your condition. So VGS minus VT will be this 5 volt minus 3 volts. And what is VDS? So here you can also plug in the ID 0.5 milliamp to this VD. So this VD will be 10 minus 3. So you will get 7 volts to the VD. Then VDS will be 7 minus 3. So VDS is 4 volts. Minus VT. So you will see that this is indeed in the saturation. You need to verify this. So then this is a valid solution. And this is saturation region.
We assumed it to be saturation.
Yes.
Could be triode as well.
So the circuit will only have one stable configuration. So if this transistor here is in, due to those voltage bias, if this transistor is in the saturation, it will be only in the saturation. Or in other words, if here you start with your assumption, like triode region, you use that equation, and then you calculate those, and then you get some solution for your ID, and then you can back check, you will find out that that's invalid as well. So the circuit will only have one condition, one operation, given the bias. So any questions here? All right, so you can further review this by watching the video in the YouTube to review the process of solving this question. Okay, so far we talked about the NMOS, N-type MOSFET. Now let's talk about the P-type MOSFET or PMOS. So PMOS, first of all, everything is reversed from the NMOS. For example, if you look at the structure of the PMOS, the substrate will become N-type, and then the source and the drain doping will become P+. So this is exactly opposite to the NMOS. And in the PMOS, actually then after the inversion, you will create a P-type channel with holes moving. And also from the circuit symbol here, you will notice that for the PMOS, all the voltages are negative. So for example here, this side is attached to the power supply VDD, and this bottom side is ground. So the definition of the source and drain is also reversed. So if you recall the NMOS, the current is flow from the drain to the source. However, in the PMOS here, the current is flow from source to the drain. And now this becomes the VGS, and then this becomes the VDS. So the VGS will become a negative value. VDS is also a negative value. And then you will also have the threshold voltage as used VTP, represents the threshold voltage for the PMOS. It's also a negative value. And actually, to turn on this PMOS, you need a VGS even further negative than VTP. So everything is reversed in the PMOS. So sometimes this will be confusing to you. So here, a suggestion to make it easier for you is to treat the PMOS same as NMOS if you take all the voltage difference as absolute value. So that means, for example, you can still apply the current, like the trial region current or the saturation current. For example, here the saturation current. You can still apply the same current, but you need to take the absolute value of all those voltages. So here, for example, the saturation current. So Vs, ideally you need to use Vsg, because everything is reversed. But you can still use Vgs if you take the absolute value. And then use absolute value of Vtp. Then you can have the same equation as before. The only thing you need to change here is from the Kn to Bkp. So essentially change from the mu p to mu n, the mobility, mu n to mu p, the mobility from the electron to the hole. Then you can apply the same equation. Similarly, you can do the saturation, the child region. If you take the difference as absolute value. Or let's look at some example. For example, here the Vd, let's say is 1 volt. And then this gate voltage, for example, 0.3 volts. And here is ground. And your Vtp is negative 0.5 volts. So you want to take everything as absolute value. So Vgs, if you look at what is actual Vgs, it is negative 0.7. Right? Because this 0.3 minus s minus 1, you will get negative 0.7. And then Vds will be 0 minus 1, you get negative 1 volt. So Vtp is 0.5 volts. So everything is negative. So here Vgs is negative, Vds is negative, and Vtp is negative. But if you want to get the current, you can take all the absolute values of those numbers and then plug in to those equations here. Follow the same equation as NMOS if you take those absolute values. Any questions?
So for sake of getting the same current, the same direction of current, we are taking the absolute values only for that purpose. Otherwise, VGS and all are negative.
Yes.
So it's just for the purpose of the current, drain to source current. If the current flows from drain to source.
No. For PMOS, current is flowing from source to the drain. Actually, your current is also elective if you use the same definition as NMOS. NMOS is drain to the source. If you use definition of NMOS current flow, then the PMOS current will also become negative value if you use drain to the source as a definition. But here, since we use source to drain for the PMOS current, then you get positive current. It's just a matter of definition. But I mean, for the value or the amplitude of the current, you can use this equation if you use all the positive absolute values plug into the equation. But the current definition, you need to be careful. For the PMOS, it's source to the drain. Or in other words, for the PMOS, it's higher potential to the lower potential. That is always true for the current. So here you say the PMOS is source to the drain. Why source to the drain? Because source is 1 volt, drain is ground. Of course, current is from the higher potential to the lower potential. But by definition, in the PMOS, it's from source to the drain. If you compare with NMOS case, it's drain to source. Of course, it's drain to source because drain is higher potential in the NMOS. right? So it's just a matter of definition. But for the amplitudes, you can always use those two equations, and then plug in the voltage with the absolute values.